Welcome to This Explainer. Okay, let's dive right into this. Have you ever paused and just wondered what the invisible engine is that truly powers our modern, hyper-connected world? Today we're looking at discrete mathematics, specifically functions and graph theory. Now I know to some of us that might sound a bit dry or, overly academic on the surface. But stick with me here, because this is literally the architecture that makes our physical and digital reality function seamlessly. We're going to unpack exactly how these foundational concepts model complex relationships and analyze the connectivity that's all around us.
So think about it for a second. How exactly does a robot know its path through a massively crowded warehouse? Or how does a global network secure your private data? It's not magic, and it's certainly not just trial and error. It is pure, structured math. These concepts are high-stakes tools that solve massive global problems. Whether it's keeping your bank account safe from bad actors or guiding a delivery drone right to your front door without wasting a single ounce of battery, the mathematical theories we're about to unpack are really the silent guardians and the unseen navigators of our modern age.
Here is our roadmap for today. 1. Types and mechanics of functions. 2. Paths, circuits, and planar graphs. 3. Applications in tech and logistics. And 4. Ethics in mathematical modeling.
All right, let's get started with Section 1, Types and Mechanics of Functions.
First up, we've got the injective function. An injective function means each element of the range is mapped to by at most one element of the domain. You can basically think of it as a strict no-sharing rule. Every single input gets a unique, distinct output, and absolutely no two inputs can ever point to the same destination. It's incredibly precise. Imagine assigning unique user IDs in a database, right? You absolutely need an injective function to guarantee distinct identities within that system, just so your data doesn't accidentally get crossed with someone else's. Next, we have the surjective function. Here, every element of the range is mapped to by at least one element of the domain. So if the injective function was all about uniqueness, the surjective function is all about completeness. It ensures that every possible output in a system is covered and accounted for. Nothing is left empty, no destination is unreached. In a real-world scenario, it's kind of like making sure every single task on a massive project board is assigned to at least one worker.
Now, what happens when you bring those two together? You get a bijective function. This is a perfect one-to-one correspondence where the function is both injective and surjective. And why does this matter so much? Because a bijective function gives us flawless, reversible mappings. This exact property is the bedrock of secure cryptography. If you want to encrypt a private message into an unreadable secret code and then decrypt it right back to the original message, you are entirely depending on the mathematical guarantee of a bijective function.
Let's move on and see how this builds, because these basic tools actually scale up to solve complex, real-world problems in 3 main steps. Step 1 relies on defining those base functions we just talked about. Step 2 layers them together through the composition of functions, chaining multiple operations together in a sequence, while relying on identity functions to maintain baseline states. And finally, Step 3 leverages reversibility via inverse functions. Honestly, every single time you log into a secure website or retrieve encrypted data, you are relying on these composed and inverse functions working flawlessly in the background.
Moving right along to Section 2, Paths, Circuits, and Planar Graphs.
Now, what's really interesting here is how easy it is to mix these next two concepts up. On one side, Euler paths and circuits focus on the routes, visiting every edge exactly once. Think of a city snowplow, right? Its goal is an Euler path because it needs to drive down and clear every single street without wasting gas retracing its steps. But on the other side, we have Hamiltonian paths and circuits. These focus on the destinations, visiting every single vertex or point exactly once. Think of a delivery driver who needs to drop off packages at 10 specific houses without ever visiting the same house twice. It's the difference between prioritizing the journey along the edges versus prioritizing the destination points at the vertices. Knowing exactly which theorem to apply is absolutely crucial for routing networks efficiently. Building on those routing paths, we hit the concept of the planar graph. This is a graph that can be drawn out on a flat, two-dimensional surface without any of its edges crossing over one another. Mastering this concept is what allows modern engineers to analyze extremely complex connectivity in graph-based problems. Whether you're designing a microscopic, multi-layered printed circuit board for a next-generation computer chip or laying out the tracks for a massive new metropolitan subway system, ensuring your paths don't cross and cause a collision is a planar graph problem at its very core. Because let's be real, failing a planar graph problem means your shiny new subway system suddenly becomes a very expensive crash site.
Let's jump into Section 3, Applications in Tech and Logistics.
And this brilliantly illustrates exactly where these invisible concepts live in our daily lives. Composite and inverse functions, they are seamlessly applied to cryptography and security. Those strict bijective rules we talked about are what ensure your data stays locked and unlockable only by you. Moving down, Euler graphs powerfully drive network routing and transportation. When literally millions of data packets travel across the global internet every second, Euler theorems help the algorithms find the most efficient pathways. And finally, Hamiltonian graphs are essential for robotics and intelligent systems, ensuring an automated robot can navigate a massive warehouse to collect items efficiently, all without wasting battery life, revisiting the same locations. When you really look at the sheer scale of this, it's pretty wild. These applications are everywhere. Real-life network routing for our global communications, international logistics and transportation networks, highly sophisticated path planning and navigation systems in our phones, and real-time decision-making in advanced robotics. We are actively building self-learning applications and artificial intelligence systems that completely rely on these mathematical principles to navigate our physical world. Every single time an autonomous vehicle makes a split-second routing decision, it is dynamically solving Euler and Hamiltonian problems much, much faster than humanly possible.
Which brings us to our final section, Section 4, Ethics in Mathematical Modeling.
The foundation of the source material we're exploring today explicitly states a really important mandate. I actually want to read this direct quote from the learning outcomes. Develop and analyze inverse and composite function-based solutions with social and ethical responsibility. This isn't just a nice afterthought, you know. It is a primary mandatory outcome. When we build these powerful models for global cryptography or resource routing, we're actively making decisions that affect human privacy, physical safety, and societal equity. The mathematics itself might be totally objective, but the way we choose to deploy it, that involves deeply human choices.
So the crucial point is that writing an algorithm isn't just a simple math problem. It's a profound social responsibility. Building secure network and cryptography models requires tremendous algorithmic integrity and deep ethical foresight. Think about it. If an inverse function is used to decrypt highly sensitive private data, well, who is trusted with the key? If a routing algorithm based on a Hamiltonian path decides how emergency resources are distributed during a crisis, is it treating all neighborhoods fairly? We have to ensure we design secure, ethical models that truly protect individuals and elevate society as a whole.
Which leaves us with this final, vital thought. As we continue to build the intelligent, autonomous systems of tomorrow, how will you use these mathematical foundations to shape a world that isn't just incredibly efficient, but highly ethical? Discrete mathematics, from the rigidity of bijective functions to the elegance of Hamiltonian circuits, truly is the invisible engine of our future. Thank you so much for joining me for this explainer. Keep exploring and always keep questioning the algorithms that shape our world.